Welcome to the contribution about computational sensitivity analysis in the design process of pre-stressed lightweight structures. My name is Martin Fusseder. I work for the Chair of Structural Analysis, Technical University of Munich. Let's start with the question what sensitivity analysis is. So typically we deal with a model which can be a structural analysis model, which is input parameters like stiffness or load parameters or geometrical properties. And these are connected by the model with model responses like displacements or stresses, for instance. And in sensitivity analysis, we deal with studying the effects of varied input parameters to the variation of the response. There are several ways to describe the sensitivity. What we do is local sensitivity analysis, which means we describe the relation between R and SI with a derivative. There are several computational approaches to compute the derivatives, and what we use is adjoint sensitivity analysis, and it can be seen as the generalization of the method of influence function. This issue is discussed more in detail in the paper. The method of influence function is a very traditional and well-known tool in structural engineering. Here in this table, we compare this classical approach with the generalized approach based on adjoint sensitivity analysis. We can see that both approaches are equivalent two-step approaches. In the first step, the influence function corresponding to the response is computed. In the classical approach, this is done by application of the so-called dual load, whereas in adjoint sensitivity analysis, the influence function is determined by solving the adjoint problem. In the second step, in the classical method, physical loads F are evaluated on the influence function eta, whereas in the generalized approach, some parameter-dependent pseudo-loads F star are evaluated on the influence function. The only formal difference between the two methods is this derivative here, the R dSi, but in a lot of practical situations, this derivative vanishes. As a result, the classical method delivers the functional value due to the load F, whereas in the generalized approach, only the derivative can be computed. This is due to the fact that between general responses and parameters is in general a nonlinear relation, which means the principle of superposition is not valid. Let's continue with the application of the method. In the following, we will use sensitivity analysis to investigate this cable net bridge, which is very flexible. You can see it here. We have already 25 centimeters of vertical deflection through to regular pedestrian loading. In detail, we will use the normal force N here in the main bearing cable as a response for sensitivity analysis. And during sensitivity analysis, the bridge is subjected to this load combination here. So we have pre-stress, dead load, pedestrian load, and wind load. And you can see it here in the indices. We have load in the three spatial directions. There are several ways to apply the load. In this contribution, we discussed two alternatives. In alternative A, pre-stress and dead load is applied completely initially, whereas the varying loads applied stepwise. In contrast to that, in option B, only pre-stress is applied initially, and dead load and the varying loads applied stepwise. Here in this diagram, you can see the evaluation of the normal force N during load application, which is described here by the load factor lambda. And already here in this diagram, you can see that the way of applying load is crucial on the observable nonlinearity of the response normal force. In the following, we like to investigate this even a bit more, and we like to study which contribution the individual loads have on this observable load-bearing behavior. Therefore, we use sensitivity analysis, and the sensitivities will be shown here in these diagrams, where on the x-axis we have the load factor, and on the y-axis there will be the derivatives. Which means these diagrams show us the development of the derivatives during load application. The first derivative we like to observe is the derivative with respect to the load factor lambda, which means these are the derivatives of these two curves here. And clearly we can see that through the stepwise load application of the dead load, some artificial nonlinearity is introduced. With sensitivity analysis, we get even more information, since it is possible to separate between the contribution of the individual loads in the different spatial direction on the overall derivative. And we can see clearly that the derivatives of the loads in z direction are dominating the overall derivative, which means the loads in z direction dominate the overall load-bearing behavior as well. Even more, we can see that the derivatives with respect to the loads in z direction are decreasing, which means in a derivative-based point of view, there is an underlinear relation between the loads in z direction and the normal force. This can be mechanically interpreted as the stiffening behavior of the bearing cables. But we can also observe that the derivatives of the loads in x and y direction are increasing, which means in a derivative-based point of view, there is an overlinear relation between normal force and these loads. We can also compute sensitivities with respect to other parameters, like the load intensity itself, and here we can observe the same. The derivatives of the loads in z direction are dominating and are decreasing, whereas the derivatives of loads in x and y direction are increasing. This was a very brief introduction into my work. Now I am looking forward for the discussion. Thank you very much.